Welcome! In this session, we'll be diving into the problem number 166, fraction to recurring decimal. This is a fascinating problem that combines concepts of mathematics and programming to convert fractions into their decimal representation, including handling recurring decimals. Let's get started. The problem asks us to convert a fraction, represented by two integers, the numerator and the denominator, into its decimal form. If the decimal representation has a repeating part, we need to enclose that repeating sequence in parentheses. For example, if the fraction is 2 over 3, the result would be 0, 6, with the repeating digit 6 inside parentheses. On the other hand, if the result has no repeating part, like 1 over 2, which equals 0.5, we simply return it as is. Additionally, if the fraction simplifies to an integer, we should omit the decimal entirely. The input consists of two integers, the numerator and the denominator. The denominator cannot be 0, as division by 0 is undefined. The output is a single string that represents the decimal form of the fraction. This makes it necessary to correctly handle repeating decimals, non-repeating decimals, and integers, depending on the input provided. For the first example, consider a numerator of 1 and a denominator of 2. Dividing 1 by 2 gives 0.5, which is a non-repeating decimal. Therefore, the output is simply the string 0.5. In the second example, we have a numerator of 2 and a denominator of 3. Dividing 2 by 3 results in 0.666, where the digit 6 repeats indefinitely. To represent this repeating decimal, we enclose the repeating part in parentheses, giving us the output 0, 6. These examples demonstrate how the output format changes based on whether the decimal has a repeating part or not. Now, for more examples, if the numerator is 4 and the denominator is 333, dividing them gives 0.012012012, where the sequence 012 repeats indefinitely. This means the output should be formatted as 0, 012. On the other hand, if the numerator is 1 and the denominator is 5, the result is 0.2, which is a non-repeating decimal. Since there's no repetition in this case, the output is simply 0.2. These examples further illustrate how to identify and handle both repeating and non-repeating cases appropriately. The problem comes with several constraints and edge cases to consider. First, both numerator and denominator are 32-bit signed integers, and the denominator is never 0. The result must also fit within the 32-bit signed integer range. It's important to manage negative values correctly. For instance, if one of the inputs is negative, the result will be negative, but if both inputs are negative, their signs cancel out, and the result is positive. For example, dividing -1 by 2 results in -0.5, but dividing -1 by -2 results in 0.5. Additionally, if the numerator is 0, the output is always 0, regardless of the denominator. There are a few more cases to handle. For repeating decimals, such as 1 over 6, which equals 0.1666, we enclose the repeating part, resulting in 0.16. For non-repeating decimals, like 1 over 4, which equals 0.25, we simply return the result as is, without parentheses. Finally, it's crucial to handle large numbers within the 32-bit range. For instance, 214,748,3647 over 1 should return 214,748,3647, and -214,748,3648 over -1 should return 214,748,3648. In all cases, the output must be a valid decimal string, with parentheses used only for repeating sequences. Handling these edge cases ensures the solution is robust and accurate. When tackling this problem, one intuitive approach might be to perform long division step by step, appending each digit to the result as we go. The idea would be to detect a repeating cycle by noticing when a remainder appears for the second time. This would allow us to split the decimal into two parts, the non-repeating portion and the repeating portion. However, this brute force method quickly runs into issues. For one, it doesn't efficiently track the remainders, making it cumbersome to detect the recurrence accurately. Additionally, if the repeating cycle starts after many digits or is particularly long, the method becomes inefficient and prone to infinite loops. Lastly, for large denominators, the approach struggles with performance, making it impractical for real-world scenarios. These limitations prompt us to explore more robust strategies. To address the inefficiencies of the brute force approach, we turn to a hash map-based optimized strategy. The key insight here is to store each remainder we encounter during the division along with its position in the fractional part of the result. This allows us to immediately detect when a remainder repeats, indicating the start of a recurring cycle. The process begins by handling edge cases, such as when the numerator or denominator is 0, or when the signs of the numbers differ. Next, we calculate the whole number part through integer division and initialize the fractional part. As we perform the division for the fractional portion, we use the hash map to track each remainder. If a remainder repeats, we can pinpoint its position in the result and enclose the recurring section in parentheses. This approach is efficient, with a time complexity of O(n), where n is the number of unique remainders, and a space complexity of O(n) for the hash map. Additionally, while there is an alternative strategy that relies on string manipulation to detect cycles, it is less efficient due to the overhead of managing strings for large inputs, making the hash map-based approach the clear choice. The hash map-based optimized approach stands out as the chosen strategy because it strikes a balance between efficiency and simplicity. By leveraging a hash map to map remainders to their respective positions, we can efficiently detect recurrence without unnecessary complexity. This method avoids the pitfalls of the brute force approach, such as infinite loops and inefficiency, and sidesteps the added complexity of string manipulation. The space complexity of O(n) is a worthwhile trade-off, as it allows us to handle cases with long recurring cycles effectively. A key realization here is that the behavior of the decimal expansion is entirely determined by the remainders during division. Once a remainder repeats, the sequence of digits also begins to repeat. This insight, combined with the ability of the hash map to track remainders and their positions, provides a clean and scalable solution to the problem. When comparing the various approaches, the trade-offs become apparent. The brute force method, while simple to implement, fails to handle edge cases and is computationally inefficient. The string manipulation approach, while feasible, adds unnecessary complexity without offering significant advantages over the hash map-based method. In contrast, the hash map-based approach effectively balances simplicity and performance, making it the ideal choice. By efficiently tracking remainders and their positions, it addresses the core challenge of detecting recurring cycles in the division process. This ensures an optimized and elegant solution to representing fractions as recurring decimals, making it the most robust and practical strategy for this problem. The problem we are solving involves converting the division of two integers, numerator and denominator, into its decimal representation as a string. If the decimal contains a recurring cycle, we enclose that cycle in parentheses. To approach this, we first handle edge cases. For example, if the numerator is 0, the result is simply 0, and we can return it immediately. Next, we determine the sign of the result. If the numerator and denominator have different signs, the result will be negative, so we prepend a minus sign to the result string. For simplicity, we work with the absolute values of the numerator and denominator. Once that's done, we compute the integer part of the division using integer division and append it to our result string. Finally, we check the remainder. If the remainder is 0, there's no fractional or recurring part, and we can return the result string as is. If there is a remainder, we proceed to compute the fractional part. To do this, we append a decimal point to the result string and initialize a hash map, or dictionary, to track remainders. The key in this hash map will be the remainder, and the value is the index in the result string where this remainder first appeared. Now, we iterate as long as the remainder is not 0. If the remainder is found in the hash map, it means a recurring cycle has been detected. Using the index stored in the hash map, we can insert parentheses around the recurring part in the result string and return the result. If the remainder is new, we store it in the hash map along with its current index in the result string. Then, we multiply the remainder by 10 to compute the next digit in the fractional part. By performing integer division with this new value, we get the next digit and append it to the result string. Finally, we update the remainder using the modulo operation, and the process repeats until we either detect a cycle or the remainder becomes 0. The core insight behind this algorithm is understanding that recurring cycles in the decimal representation occur when the same remainder reappears during the long division process. By tracking remainders with a hash map, we can efficiently detect cycles and handle them. This hash map provides constant time lookups, ensuring the algorithm's efficiency even for large inputs. Additionally, by determining the sign of the result upfront and working with absolute values, we simplify the computation and avoid potential errors related to sign handling. To implement this solution, we use two main data structures: a string to build the result incrementally, handling both the integer and fractional parts, and a hash map to track remainders and their positions in the result string. This combination allows us to detect and manage recurring cycles effectively. At the heart of this algorithm are several key operations. Integer division and the modulo operation are performed during each step of the long division process, and both run in constant time, O(1). Similarly, operations on the hash map, such as inserting and looking up remainders, also run in O(1). As a result, the overall time complexity of the algorithm is O(n), where n is the length of the recurring cycle or the total number of digits in the fractional part. Each remainder is processed at most once, ensuring the algorithm remains efficient. To illustrate these concepts, let's walk through an example where the numerator is 4 and the denominator is 333. This will demonstrate how the algorithm computes both the integer and fractional parts, detects cycles, and constructs the final result. For the given example, we start by computing the integer part. 4 divided by 333 gives 0, so the initial result is 0. Next, we calculate the remainder, which is 4, and begin processing the fractional part. The remainder is multiplied by 10, giving 40. Dividing 40 by 333 yields 0, so we append 0 to the result. The remainder is now 40, and we store it in the hash map. Repeating this process, we eventually see the same remainder, 40, appear again. This indicates a recurring cycle. Using the hash map, we identify where the cycle starts and enclose the recurring digits in parentheses. The final result for this input is 0, 0, 12. This demonstrates how the algorithm handles both the decimal construction and recurring cycle detection seamlessly. Here, we begin by defining the fraction to decimal method within the solution class. The first thing we check is whether the numerator is 0, because if it is, the result of the fraction will always be 0, and we can simply return that as a string. Next, we initialize an empty list called result to build the final output as a sequence of characters. To handle the sign of the result, we use the XOR operator to check if either the numerator or denominator is negative, but not both. If this condition is true, we append a negative sign to our result. Then, we convert both the numerator and denominator to their absolute values to simplify the calculation. After that, we calculate the integer part of the division using floor division and append it to the result as a string. We also calculate the remainder using the modulus operator. If the remainder is 0, it means the division is exact, and we can return the result as a joined string immediately. However, if there is a remainder, it indicates we have a fractional part to handle, so we append a decimal point to the result and set up a dictionary called remainder_map to keep track of remainders we encounter as we process the decimal part. Now, we enter a while loop that continues as long as the remainder is not 0. The first step inside the loop is to check if the current remainder has already been seen in remainder_map. If it has, this indicates the start of a recurring cycle in the decimal, so we insert an opening parenthesis at the position stored in the map and append a closing parenthesis to the result before breaking out of the loop. If the remainder is not yet in the map, we record its position in the result list by mapping it to the current length of the list. Then, we multiply the remainder by 10 to simulate moving to the next decimal place. Using floor division, we calculate the next digit of the fractional part and append it to the result. After this, we update the remainder using the modulus operator. Once the loop finishes, we join all parts of the result list into a single string and return it. This approach ensures we correctly handle both terminating and repeating decimals. To start, we import necessary packages and define the solution class with the method fraction to decimal. The first step in the method is to handle the edge case where the numerator is 0. If it is, we simply return 0 as the result. Next, we initialize a string builder to construct our result incrementally. Then, we determine the sign of the result by checking if the numerator and denominator have opposite signs using the XOR operator. If they do, we append a negative sign to the result. After that, we convert both the numerator and denominator to their absolute values. This ensures that we work with positive numbers for the rest of the calculations. The integer part of the division is calculated by performing integer division of the numerator by the denominator, and this value is appended to the result. Finally, we compute the remainder of the division. If the remainder is 0 at this point, it means the division has no fractional part, and we can directly return the result as it is. Now, if there is a non-zero remainder, we proceed to handle the fractional part. We append a decimal point to the result and use a hash map to track remainders we've seen before, mapping each remainder to its corresponding position in the result. This helps us detect recurring cycles. While the remainder is not 0, we first check if it already exists in the map. If it does, it means we've found a recurring decimal. To represent this, we insert an opening parenthesis at the position stored in the map and append a closing parenthesis at the end. This breaks the loop and finalizes the result. If the remainder is not yet in the map, we store its position in the result, multiply it by 10 for the next digit, and append the result of dividing this new remainder by the denominator. We then update the remainder using the modulus operator. Once the loop completes or a recurring pattern is detected, we return the constructed result as a string. Let's start with the example where the numerator is 1 and the denominator is 2. First, we check if the numerator is 0. Since it's not, we proceed. Next, we determine the sign of the result. Both the numerator and denominator are positive, so the result will not have a negative sign. We then take the absolute values of both numbers, which remain the same, numerator is 1 and denominator is 2. Now, we perform integer division, dividing 1 by 2, which gives 0. This is added to our result list as the first digit. After this, we calculate the remainder, which is 1 modulo 2, resulting in 1. Since the remainder is not 0, it indicates there's a fractional part, so we append a decimal point to the result list. To handle the fractional part, we initialize a map to keep track of remainders and their positions. We multiply the remainder by 10, yielding 10, and divide it by 2, obtaining 5. This is appended to the result list. Finally, we update the remainder, which is now 0, meaning there's no more fractional part to compute, and the loop terminates. The result list, containing 0, and 5, is joined into the final output string, 0.5. Now, let's analyze the case where the numerator is 2 and the denominator is 3. Again, we start by confirming that the numerator is not 0, so we move forward. Both numbers are positive, so the result will not include a negative sign. Taking their absolute values, the numerator remains 2, and the denominator remains 3. Performing integer division, 2 divided by 3 gives 0, which is added to the result list. The remainder is calculated as 2 modulo 3, resulting in 2. Since the remainder isn't 0, we add a decimal point to the result list. To handle the fractional part, we initialize an empty remainder map. Multiplying the remainder by 10 gives 20, which, when divided by 3, yields 6. We append this to the result list. The remainder now becomes 20 modulo 3, which is 2. At this point, we notice that the remainder of 2 already exists in our remainder map, indicating the start of a recurring cycle. We use the position stored in the map to insert an opening parenthesis before the recurring part and append a closing parenthesis at the end. This finalizes the result as 0, 6, where the repeating part is enclosed in parentheses. In this example, the numerator is -50, and the denominator is 8. We begin by checking if the numerator is 0. Since it's not, we proceed. Here, the numerator is negative, and the denominator is positive, so the result will have a negative sign. We add a dash to the result list. Next, we take the absolute values of both numbers, the numerator becomes 50, and the denominator remains 8. Performing integer division, 50 divided by 8 gives 6, which is added to the result list. The remainder is calculated as 50 modulo 8, resulting in 2. Since the remainder isn't 0, we append a decimal point to the result list. To compute the fractional part, we initialize an empty remainder map. Multiplying the remainder by 10 gives 20, which, when divided by 8, yields 2. We append this to the result list and update the remainder to 20 modulo 8, which is 4. Multiplying this remainder by 10 gives 40, which, when divided by 8, results in 5. We append this to the result list and update the remainder to 40 modulo 8, which is 0. Since the remainder is now 0, we terminate the loop. Joining the result list, which contains dash, 6, 2, and 5, gives the final output, minus 6.25. When analyzing the time complexity of the fraction to decimal function, we can break it into distinct components. First, the integer division, represented by numerator / denominator, is a straightforward arithmetic operation. This computation takes constant time, 1. Similarly, calculating the initial remainder using numerator % denominator is also a basic arithmetic operation, which again takes 1. If the division is exact, meaning there is no remainder, the function immediately returns the result. In such cases, the overall time complexity remains 1, as no additional steps are required. Now, when the remainder is non-zero, the function has to handle the fractional part, and this is where the recurring cycle detection comes into play. The while loop processes one digit of the fractional part during each iteration. Within the loop, we calculate the next digit by multiplying the remainder by 10 and performing integer division, which is an 1 operation. Then, the remainder is updated using the modulo operation, which is also 1. To detect cycles, we use a dictionary called remainder_map to store and look up remainders, with each operation taking 1 on average. The key factor here is the number of unique remainders, which is at most denominator 1 because the remainder must always be smaller than the denominator. This means the loop executes at most denominator iterations, making it the most significant contributor to the time complexity. When considering the space complexity, the primary contributors are the data structures used to store intermediate results. The result list holds the digits of the decimal representation, and in the worst case, its size depends on the number of unique remainders, which is at most denominator 1. This gives it a space complexity of d, where d is the number of unique remainders. Additionally, the dictionary remainder_map is used to track the position of each remainder in the result. Since it also stores at most denominator 1 entries, it has the same space complexity of d. Other variables, such as numerator, denominator, and remainder, require constant space, or 1. Therefore, the total space complexity of the function is d, where d is the number of unique remainders. Let's break down the best, average, and worst cases for this function. The best case occurs when there is no fractional part, meaning the remainder is 0 after the initial division. In such cases, the function exits early, resulting in a time complexity of 1 and constant space usage. In the average case, a fractional part exists, and the function processes the unique remainders to build the decimal representation. Here, the time complexity is d, where d is the number of unique remainders, and the space complexity is also d. The worst case happens when the fractional part has a long recurring cycle, requiring the maximum number of iterations, which is denominator 1. Even in this scenario, the time and space complexities remain d, making the function robust and efficient. Comparing this implementation to a brute force approach highlights its efficiency. A naive method might involve repeatedly dividing and appending digits without checking for recurring cycles. This would lead to an infinite loop for repeating decimals, making the approach impractical. In contrast, the optimized solution uses a dictionary, remainder_map, to detect recurring cycles efficiently, with each lookup and insertion taking 1 on average. This ensures the function halts correctly, even for recurring decimals. By bounding the complexity to the number of unique remainders, the current implementation is far more efficient and reliable than a brute force method. To solidify our understanding, let's consider the mathematical proof for the big O complexities. The number of unique remainders is always less than the denominator, meaning there are at most denominator 1 unique remainders. Since each iteration of the while loop processes 1 unique remainder, the total number of iterations is bounded by denominator. During each iteration, only a constant amount of work is performed, including arithmetic operations and dictionary lookups, which ensures the overall time complexity is d. Similarly, the space complexity arises from storing unique remainders in the dictionary and the result list, both of which are bounded by O(d). This guarantees the function remains efficient for both simple and recurring decimal representations. One common mistake when solving this problem is not identifying repeating remainders during long division. If you're performing the division and a remainder reappears, that's a clear indication that the decimal has entered a repeating cycle. Missing this pattern can lead to incomplete or incorrect results. To fix this, you can use a hash map or dictionary to store each remainder along with its position in the resulting decimal string. Then, when the same remainder appears again, you can easily identify where the cycle begins. Another frequent issue is handling edge cases incorrectly. For instance, if the numerator is 0, the output should simply be 0, or if the denominator is 1, the result is just the numerator as a string. Similarly, if the numerator is perfectly divisible by the denominator, like 4 divided by 2, the output should be a clean integer string like 2. Explicitly coding for these scenarios before diving into the main logic can save you headaches later. Finally, some people tend to overcomplicate cycle detection by using nested loops or unnecessary data structures, which can make the solution inefficient. Instead, stick to the dictionary approach for mapping remainders to positions. This keeps the cycle detection straightforward and efficient, running in linear time relative to the number of digits in the decimal expansion. Another issue to watch out for is ignoring negative numbers. If you don't correctly account for the signs of the numerator and denominator, you could end up with incorrect results. For example, dividing -1 by 2 should give -0.5, but some solutions mistakenly produce results like 0.5 or even -0-5. To avoid this, normalize the sign at the start by checking whether the numerator and denominator have different signs, and then proceed with their absolute values for the calculations. Precision errors can also arise when working with large numbers if you use floating point arithmetic instead of integer operations. Floating point calculations can introduce rounding issues, especially with very large numerators or denominators. To ensure accuracy, always stick to integer division and remainder calculations throughout the process. This problem is often used in interviews to test your ability to recognize patterns in iterative processes, such as detecting repeating remainders. Being able to articulate this insight during an interview demonstrates strong analytical thinking. Additionally, showing that you can use simple data structures, like a dictionary for remainder to position mapping, highlights your ability to write clear and efficient code without over-engineering. You should also expect follow-up questions about edge cases, such as handling inputs like 0 divided by 1, 1 divided by 0, or -1 divided by 2. Be ready to explain how your solution addresses each of these scenarios. Lastly, interviewers may ask you to discuss time complexity. The optimal approach has a time complexity of O(k), where k is the length of the decimal expansion, which is upper bounded by the denominator. Explaining why this is efficient compared to brute force solutions can further solidify your understanding of the problem. There are several related problems on LeetCode that share similar concepts or techniques. For example, LeetCode 7, Reverse Integer, also emphasizes handling edge cases when working with integers. Then, of course, there's LeetCode 166 itself, Fraction to Recurring Decimal, which directly involves implementing the repeating decimal detection logic. LeetCode 43, Multiply Strings, focuses on manipulating numbers as strings while avoiding floating point arithmetic, which is a key skill for problems like this. Finally, LeetCode 29, Divide two integers, challenges you to implement division mechanics without relying on built-in division operators, further reinforcing your understanding of integer operations. There are alternative approaches to solving this problem, each with its trade-offs. The brute force simulation approach is simple to implement but becomes inefficient for large denominators and struggles to handle repeating cycles effectively. Using floating point arithmetic might seem easier initially, but it introduces precision errors and fails for very large inputs. The optimized remainder tracking method, which involves using a dictionary to map remainders to their positions, is both efficient and precise. However, it does require a solid understanding of modular arithmetic and how to detect cycles. Finally, string manipulation can be useful for formatting the result, but relying too heavily on string operations can unnecessarily complicate the logic and make the implementation harder to debug. Great job following along. To wrap up, we've covered how to convert fractions into recurring decimals using a hash map to track remainders and detect cycles. This is a crucial technique for handling precision-based problems efficiently. Thanks for watching, and don't forget to like and subscribe for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!